Hello and welcome to our first day on sequences and series. Now, if you have some money in your piggy bank and you want to save some money for some special purpose, you get a job that pays you $13 a day. Big money. The table here gives you the amount in your bank at the end of each day. So at the end of day 1, you have 53, and so on. This is a discrete function. This is a discrete function because if I graph this, it would look something like this. To draw a line in here would be inappropriate because at day 1.5, your bank account doesn't go up somewhere between 53 and 66. At day 1 is 53, and at day 2 it jumps to 66. So it wouldn't be a good idea to draw a line connecting it. It would be discrete, which means there's just points along the way. Now we have to think, is this arithmetic or is this geometric? Arithmetic sequences go up by adding, and geometric sequences go up by multiplying. Now, do I add or do I multiply to get my next number? Well, it looks like I add 13 to each of the terms to get its next number. So now we want to find out how much money will be in the bank at the end of the 10th day. Well, we could just keep on adding this up each time. Or we could see that this one is 53 plus 13. This is 53 plus 13 plus 13, which is 53. That's not a 5. 53 plus 13 times 2. The next one would be 53 times, or plus 13 times 3. Hopefully you see a connection between this number and the number we're multiplying it by. This would be like 13 times 1. So our formula, we could say, would be 53 plus 13 times 1 less than our number up here. Right now it's 10, so I'll write in 9. So I'll take out my trusty calculator and go to this page, and it will be 53 plus 13 times 9 to get a grand total of 170. So you'd have $170 at the end of the 10th day. Find out how much money will be in the bank at the end of the 100th day. So now that we have our formula, 53 plus 13, 1 less than this would be 99. So all I have to do, I could just press second enter, add a 9 at the end, and that would be 1,340. So if I wanted to write an equation like we just did, we would take our base amount, which is 53. We want to add 13 each time by n minus 1 days. Now the common difference. The common difference is the difference between two consecutive terms, and here that common difference is 13. So now, what form of recursive formula could we use? Now, a recursive formula is a formula that relies on the previous term. So how do we get from the previous term to the next term? Well, t sub n minus 1 is our previous term, and from each previous term, we will add 13. This gets a little confusing with notation, so sometimes it helps to put in some real numbers. Let's say I'll say t is 4. T sub 4 is equal to t sub 4 minus 1 plus 13. 4 minus 1 is 3, so t sub 3 plus 13 is going to give me t sub 4. If I looked back at here, my t sub 3 is 79, so t sub 4 is going to be 79 plus 13. Or t sub 9 would be 92. The problem with recursive formula is for the recursive formula, you always need the previous term. So if I wanted to find t sub 10, that's not going to help because I don't know t sub 9. So to find t sub 10, I'm going to want to use my explicit formula, this one, because I can just plug in 10. However, if I know a term and I just want the next term, I can use the recursive formula. So this is what we call the explicit formula. I got a little ahead of myself, where we have t sub n equals 53 plus 13 times n minus 1. Now, if we have a geometric series, a better way to save money would be to put it in a savings account where you can earn interest. A baby's parents deposit $1,000 into an account on its first birthday. Its interest is 6% compounded annually. Now, 6% is a lot of interest for a savings account. Maybe a more appropriate terminology or an appropriate problem would be the parents invested in a mutual fund that gains 6% interest. But we don't need to get into the specifics in finances. But let's find t sub 2. So there's a couple ways we can do this. A lot of people, the first time they see this, they take 1,000, multiply it by 6%, which is 0.06, and they get 60. So if that is the amount of interest, the amount in the account is going to be 60 plus 1,000, or 1,060. Now, to save a little time, what we're going to do is I can take 1,000. If I multiply it by 1, I get 1,000, which is my principal. And if I multiply it by 0.06, I'm multiplying that by the interest. So if I combine these, I can just do a 1,000 times 1.06, and this is the same thing as 1,060, and that means I'm increasing by 6%. All right, so if I wanted to do these in dollars, if I have 1,000, oh, that's 11, times 1.06, I get 1,060, like we said. And now if I multiply this by 1.06, and if I keep hitting enter, now that it just has answer times 1.06, it'll keep giving me the next few values. So the next one's 1,123. I should just drag this so I don't have to worry about it. 1,123.6, 1,191.02, and then finally 1,262.48. So on the fifth year, they'll have $1,261, or $262.48. What equation would you put into your calculator in sequence mode? So what we could do is turn our calculator to sequence mode. All right, so if we put this in sequence mode, we go to mode, we come down to where we had function. Now we know a lot about this row. This is the function mode, this is the parametric mode, this is the polar mode, and this is the sequence mode. So if I hit y equals, now it's u sub n equals. This isn't the correct thing, so let's clear things out. All right. In our equation, we want our n min to be 1. And now to type in the rest, I can do u sub, which I do second. Second 7 gives you a u. So if I did u sub parentheses n minus 1, n parentheses, times 1.06. Now our starting value is 1,000. Our starting value is what we put here for the use of use of n min. So that's what I put on there. And when I hit second table, let's see if we get the same values. Oh, my table's in the wrong spot. So I'll hit second window. I'll start this at 0 and go up by 1. Now notice they give you an error at 0, but at 1 it's 1,000, 1,060, and it looks like we have the same numbers that we had before. So we can pull that in there. Now, if I wanted to graph this, well, first, this is just graphing the stat plot that I had on earlier. So let's turn off my stat plot. And now let's zoom fit and see if this works. There it is. Zoom fit, you can see this is our line right here. It looks somewhat linear, but it also looks like there's some sort of curve in it. Not a huge curve, but if I drew a straight line, I don't connect all the dots. I could do something like that, and it goes below and then goes above. But I don't think this is going to be a good predictor because it goes low and then it goes above. It might keep going above forever, and then it would go off from where my line is. So I don't like this, thinking that this is a linear model. All right. So sketch the graph of t sub n as a function of n for the first 18 birthdays. What does the model appear to be? And we didn't do 18. We did 1, 2, 3, 4, 5, 6, 7, 8, 9. If I wanted to do more, we would just have to look at the window and go up to 18 birthdays. And we'll have to extend my x up to 18. And our y has to go much higher. Let's do our y at, let's say, 3,000. That might be too low. I don't know. Let's check it out. No, it looks pretty good. So if we go out, now it even looks like there's more evidence that there's kind of a curve in that. So we have to think, what kind of a model does that look like? It looks like it's exponential, I would say. So I would say this looks like an exponential graph. Find t sub 18. All right, now t sub 18 would be tough. So let's think about how we set this up. Our first value is just 1,000. Our second value is 1,000 times 1.06. The next value will be 1,000 times 1.06 times 1.06, which is 1.06 to the n power. 1,000 times 1.06, now this would be to the third power, and then to the fourth. So we're just taking 1 from our n value. So if we want to find to the 18th power, we'd do 1,000 times 1.06 to the 17th power. Back to the trusty calculator. Or actually, we could have just looked at our calculator. This might have been easier, since it's already plugged in our sequence mode. This would be 2,692.8. Now, if I would have done this, let's see if I did my work right. If I did this just on my blank screen, if I took 1,000 times 1.06 to the 17th, looks like we get the same value. So there's a couple different ways we can get the same value. So find an explicit form. That's what I did on the previous page. The explicit form was t sub n is equal to 1,000 times 1.06 to the n minus 1. To get the next term in a geometric sequence, you simply just multiply the previous term by a constant. This constant is called a common ratio. The common ratio in this example is 1.06. All right. If we start at t sub 1, then our recursive formula for arithmetic is t sub n equals equals our previous term, which is t sub n minus 1, plus our common difference, where we start t sub 0, where we're going to start at t sub 1. And it already tells us there. Start at t sub 1. Our recursive formula for geometric, we're going to take a t sub n, and we're going to take the previous term, and we're going to multiply it by our common ratio. That's t sub n minus 1 times r. For our explicit forms, we're going to take t sub n equals our starting point plus our common difference times n minus 1. And for our explicit formula, we're going to take t sub n equals our starting point times our common difference, or our common ratio, to the n minus 1 power. Now, this you can pause, think about, what kind of sequence is this? 64 minus 48 is 16. If I take 48 minus 36, I don't get 16. So now I'm not thinking that this is addition. I think that this one might be have a common ratio. So let's do 48 divided by 64. That's 0.75. Let's do 36 divided by 48. That's also 0.75. And 27 divided by 36 is also 0.75. So our common ratio here is 0.75. So that means it's a geometric sequence. Our common ratio, we said, was 0.75. Our t sub 6, well, since we have t sub 4, I think the easiest way would be is to multiply 0.75 and then multiply by 0.75 again. So 27 times 0.75 times 0.75. So our t sub 6 would be 15.1875. So let's look for a recursive and an explicit formula for this. For a recursive formula, we're going to take our previous term and we are going to multiply it by 0.75. Now, we have to state where we start at. We're going to start at 64. Now, for an explicit formula, we're going to start at 64, and we're going to multiply it by our common ratio to the n minus 1 power. So that's our recursive. This is our explicit. Now this, we go up by 2. We go up by 4. This is an addition, not a multiplication. This we go up by 6. Now this one it's not arithmetic nor geometric. This is a quadratic function because it has constant second differences. So this one, the answer is just neither. Now if we look at this one, here we go up by 11, up by 11, up by 11. So it looks like this one's arithmetic. The common difference, we're going up 11 each time, so that's our common difference. Our recursive formula is we take our previous term, that's t sub n minus 1, and we're going to add 11 to it, and my starting term is -4. My explicit formula, we start with -4, and we add 11 times n minus 1. If we want to find t sub 15, we plug in 15 into this equation. So we have -4 plus 11 times 15. N sub 1, so hopefully you caught that that was supposed to be 14. So now we just take out our calculator, -4 plus 11 times 14, 150. So the 15th term should be 150. All right, now take some time and try to figure this out on your own. What type of sequence is this? Now 45 minus 27 is 18. 75 minus 45 is 30. So it's not arithmetic. We know that for sure. Let's check geometric. What's 45 divided by 27? What's 75 divided by 45? Looks like it's the same number. So it looks like we're multiplying by 5/3 or 1.66 each time. So that means we have a geometric sequence. Now let's find a recursive and an explicit formula for this. I would pause it and try to do it on my own. We'll take our previous term, t sub n minus 1, and we're going to multiply it by 5/3, and we'd have to say our start is at 27. Now for an explicit formula, t sub n equals our starting term, which is 27, times our common ratio to the n minus 1. This is our explicit, and this is our recursive. Find t sub 17. Now if we look back, if I wanted to use this equation, t sub 17 would equal t sub 16 times 5/3, and that works. However, I don't know t sub 16. So the easiest one to use is this formula. You plug in 17 here and find the value. So 27 times 5/3 to the 17 minus 1 would be 16. So 95,707. So t sub 17 is 95,707, rounded. Now use our function or explicit formula for the sequence to find the number of terms for the term after the first set of ellipsis marks. Now I didn't know this term until this book, actually. These are what ellipsis marks are. So now we want to find the n that corresponds to this value. All right. Well, we know our equation. T sub n is equal to 27 times 5/3 to the n minus 1. We know our t sub n is 34,454.52. First thing I would do is divide by 27 on both sides. So 34,454.52 divided by 27. 1276 is equal to 5/3 to the n minus 1. Log both sides, so we'll have the log of 1,276 is equal to log of 5/3 to the n minus 1. I could take that n minus 1, pull it out front. And then I divide by log of 5/3, so n minus 1 is equal to log of 1276 over the log of 5/3. And let's see what our calculator says. Log of 1276 divided by the log of 5/3. And it's pretty much 14. That equals n minus 1. If we add 1 to both sides, we'll get 15. So 15 is the term that this value represents. Now let's try this one. What sequence does this represent? Well, we're going up by 6 each time, so it's arithmetic. Find a recursive formula. Well, we take our previous term, and we're just going to add 6 each time with the starting term at 15. Now our explicit formula, we start with our starting term plus our common difference times n minus 1. To find t sub 56, all we have to do is plug in 56 into our equation. So we'll have 15 plus 6, it'll be 56 minus 1. So if I took out my calculator, 15 plus 6 times, hopefully you can do the math and say that's 55. So 345 equals t sub 56. Now let's use the function or explicit formula to find out which term this is. What's the n value there? So we know t sub n, which is 879, is equal to 15 plus 6 times n minus 1. Let's do the math, do the algebra. Subtracting 15 on both sides. So this would be 864 equals 6 n minus 1. Divide by 6. And 864 divided by 6 is going to be 146, unless I did that wrong in my head. 864 divided by 6. 144. Good thing I didn't keep going with that problem. Equals n minus 1, so we add 1 to both sides, so 145 is going to be our n value. All right, I hope that went fine. Here is your homework for tonight.